Yeah? And so what you see is the same angle of momentum, 0 here, plus 1, minus 1 here, as function of radius. So what you should expect and what you see indeed is the thin disk. Yes, it's obvious. There's a spiral galaxy that have a thin disk. Maximally rotating, extended. Then you would say, well, bulge. Okay, bulge. Yes, here somewhere is maybe a bulge, but what stands out is also that you need a thick disk component. Yeah, so good, we have done that. So then you can, of course, take out these orbits and actually project them on the sky. Say, for example, edge on view and see like how does the kinematics for that component look like. So here you have again the surface brightness distribution. Okay, thin disk, fine, thin. Fast rotating, good. Very low dispersion, axial, and a phase on very low dispersion. Yeah, that's what it should be. Then you go to the thick disk. Okay, it's slightly extended. Then indeed it's less rotating and less rotation and more higher dispersion. And then the bulge is tiny, compact, nearly no rotation, higher dispersion. Yeah, so it all makes sense. Well, let's compare with photometry, because we have these orbits of light, so we can convert that into a profile. So that is shown here. So this is surface brightness profile function of radius. The dots are from the Schwarzschild model, and what we've done here is we said, okay, let's take all disk stuff and let's take all the stuff below and plot it. Then you get here, and you see the solid lines are from Salodal are based on S4G, so this near infrared imaging decomposition in an exponential disk, so that's fine, and in their best fit to a photometric bulge, and that's also fine, because this is what we get, and this is the surgeon that we would fit to this. In other words, the bulge is much smaller, what we find, than what the photometric decomposition does. So this is an open question, like how, I mean, it's an interesting comparison between photometric and dynamical. Okay, so I'm sure a lot of people ask, like, can we believe this at all? Why would this work or why would this not work? So here is, and of course we're testing this. So these are our first results from the test. This is from Shenadal. We have a really nice, very detailed simulation of the Milky Way. This is the title of the paper. So we got from them that simulation, and we made mock maps out of that. We fitted those mock maps. This is the intrinsic orbital distribution you get directly from the simulation. This is the fit that comes out. So yes, there are differences. We are not able to catch somehow this very central rotating disk, because most likely we have some problem with the spatial resolution. We're of course figuring out, but overall it seems very hopeful in recovering. And here is more our different components. The solid or the curves are from the simulation, and the dots again are from the Schwarzschild. It's not yet perfect. We have to further investigate, but I think the news is that it's extremely hopeful going in that direction. Okay, so you do this for one, it's fun, and then you get, and what I do now here is this, so this is for this one galaxy as function of radius. Let's collapse this as function of radius and project, and then principally the histogram on this side. So that's one stripe here for this galaxy, and so if you then do Schwarzschild models for 200 and I think this 270, and this took less than a month, so it's feasible. Then you get suddenly from the whole range in morphology. So the ellipticals here, they are dominated by bulge-like orbits. Then you move into the S0s, you see the disk coming up, and the more you move to the spirals as piece, you see a stronger thin disk, until you come to the smaller galaxies, and then they get more dominated by a thicker disk component. It seems to be, I'm just speculating here, yes, this graph was made just before coming here. And then the interesting question, for example, we have to investigate, but there seems to be no classical bulge in the S0s. It has certainly a thick disk component, but we don't find a strong classical bulge. So there's preliminary on it, because obviously this is all ongoing. But my conclusion is that I think this is a very powerful way. Seems to be feasible on a large sample of galaxies, and doing this for many galaxies, I think I'm getting very hopeful that this will be interesting to really try to constrain a galaxy transformation mechanism. And then is my appeal to the simulators that, of course, at a certain point we would like to directly compare and test this, calibrate this with simulations, and it would be great to get that communication further going. Thank you.
Do we have Thorsten, or maybe whoever gets the microphone first? Gary?
Hi, very impressive. So I think you can do the 300, but my question would be, if you go back to the slide, as you go to more disky spiral galaxies, the degeneracies in doing the potential projection, but also dealing with the, I don't know, the colors, for example, the fact that the velocities you get from the stars are coming from a very complex set of different stellar populations. How can you basically address or get your systematics of the uncertainties associated with the numbers you get from the nice plot you showed with all the orbital structure as per galaxy and as you go along with the times? So don't question that, I guess you thought what it meant.
Yes, so the reason to do this check with simulations is to find out how robust we can do this, and of course the independence. Yes, this is one simulation with a bar in it, and we're looking at what if the bar is end-on, side-on, in between, what if, and actually the bar looks to have less effect. As the first result is the bar seems to have not a strong effect, unless of course you resolve it spatially dramatically. Yes, like with Muse, then it will have an effect. But only when you really view the bar end-on, then it can mix up some of the but this is very, very preliminary, but I think this is the way to calibrate it. So then all your questions like the tracer, you have the right tracers, it's a mixed population, dust, etc. So that's why we're also putting in, for example, near-infrared imaging, just to check like extinctions. So yes, if you have more ideas for how to calibrate this, but these are the two main channels we are doing at the moment. And yes,
Thorsten.
Yeah. On this part, we seem to have a very sudden transition of all the properties when we go to the branch.
yes.
Do you understand why this happens, and also why there is such a narrow range in numbers for the other groups? Shouldn't there be a smoother?
No, I don't fully understand, and no, I don't. I will just bluntly say, yeah, Remco can. So Remco knows because he has modeled the same way all LSTD galaxies. So it's the same plot for LSTD, and there is much more structure. So here, probably it's just a limitation of the kind of all the models we run, and not all the models have yet converged. 70% has converged, and 30%. So
Very short.
We just have to wait a little.
So the preliminary is there for a reason. The main thing that I'm worried about with this plot is the mass model. So what we don't resolve the plot is in the zeros yet. And so that's why there's a way. So I think, but this is exactly why.
Okay, let's thank the lab again.